Alright, so wanted to look at the tangent line to a trig function and understand that. I know in geometry when you're dealing with circles, kind of the definition of the tangent was it'll only ever intersect at exactly one point. Okay? Understand that when we're talking about calculus, like here with tangent, it looks something like this. Obviously, if I have a tangent here, it's only going to intersect at that exact point, but because this curves around, the tangent curves back around, it does end up hitting at other places. That's okay, alright? In fact, one of the applications we're going to look at today is to figure out, hey, where else would it hit? But here we have the problem, find the equation of the tangent to y equals tangent of x at the point where x is pi over 4. So, if I want the equation of the tangent line, I need the slope of the tangent line first. I also need the point pi over 4 something, okay? Well, what is that something, by the way? What's tangent of pi over 4?
Yeah, I got nothing. I don't know why I pretend to.
What's sine of pi over 4?
Sine of pi over 4, that is 30 is pi over 6, 16.
45 is pi over 4.
Yeah.
So when isn't it 1?
Tangent's 1, yeah, because you have sine is root 2 over 2, cosine's root 2 over 2, so tangent sine over cosine. So this is the point pi over 4, 1. Alright. So now the slope of the tangent line we need, what are we going to do?
Plug it in.
Plug what in?
Find the equation of the tangent.
If I need the slope of the tangent line,
Find the derivative.
find the derivative, okay? What is the derivative of tangent?
I got it.
A little rusty on these, huh?
I'm gonna say cosecant squared x.
Close. Secant squared x. Okay. Secant squared x. Remember Pythagorean identities, 1 plus tangent squared equals secant squared?
Yeah.
They go together here as well. Tangent and secant go together, cosecant and cotangent go together in pairs, and sine and cosine go together in pairs. So this is secant squared, so now I need to find the secant squared of pi over 4. Okay, so if I plug in pi over 4, how am I going to figure that out? Oh, unit circle.
Oh, so secant is
1 over
1 over
cosine.
cosine.
Okay, so it's 1 over cosine squared of pi over 4. What's cosine of pi over 4?
Root 2 over 2.
It's root 2 over 2. And I got to square that now.
So it's gonna
2 over 4, that's 1/2, right?
Yep, that's going to be 2 over 4. And it's 1 over 2 over 4. So 1 over a half is
2.
2. Alright? So, the slope of the tangent line equals 2. Now we can find our equation. Y minus 1 equals 2 times x minus pi over 4. And we get y equals 2x minus pi over 2 plus 1. You don't need to change that to a decimal to actually combine them or anything, unless you were actually wanting to graph it and you had to get an idea of where that was. Okay, but that's your equation. Okay? Don't forget to keep reviewing, keep that unit circle in your mind. Okay, that unit circle, they expect you to know. This problem could very easily be on a no calculator, on a paper 1 part of the exam.
In this case, we got a slope that happens to be a whole number, but just using just secant and trig function, I just feel like most of them are going to be decimals.
Well, yeah, I mean, if we just
do we keep it in trig?
Well, if we just picked an angle at random, yes. Because we got an angle that was on the unit circle, it came out to look nice. Okay. But yeah, we could apply the same thing if it was find the equation of the tangent at the point where x is, 1.2 radians, then yeah, at that point we're using our calculator and doing that stuff. So alright, so there's a couple of other applications that we could have here. First of all, finding where a tangent meets a curve a second time. Okay, or possibly a second and third time, depending on what it is, okay? So here we have a cubic equation, a y equals x cubed plus x plus 2, okay? Alright, so that's going to look something like this. It actually comes down kind of like that, and it's hitting somewhere between 1 and 2 down here, or -1, -2. Okay. Now the 0.14 is going to be way up here. I'll go ahead and just say that it's here, and the idea is this. We're going to draw the tangent line here, and if I continued to draw that tangent line, it would hit this function a second time somewhere. Alright? Now the sketch is nice because it's going to give us some idea of where it would be. I know it looks like x and y will probably both be negative. Okay? But we're not exactly sure just by looking. So what overall strategy am I going to need to use in order to figure this out?
Find the equation of the line.
Alright, good start. Let's find the equation of the line. So dy dx is 3x squared plus 1. If I plug a 1 in, then the slope of my tangent line is going to be 4. Alright, so the tangent line, the tangent is y minus 4 equals 4 times x minus 1. So it's going to be y equals 4x. Okay, so this actually should be hitting the origin, but it's okay for right now. Alright, so now what do we do?
Now you just gotta graph the other one. And the point of intersection.
Do we find?
We have to find a point of intersection.
Do we, okay, so basically could we say that if we set y over x, would it be equal to 4? Because it would have the same slope, so we need to find another point. You know what I'm saying?
Yeah, I get what you're saying. There's a simpler thing here.
Yeah, that'd be so complicated.
We want an intersection of two curves, right?
Yeah.
How do we find that?
Oh, trace, on the graphing calculator, you put both equations.
Put both equations in, and you calculate where they intersect, okay? How do we find intersections without the calculator doing it for us? Prayer.
No, wait, I remember.
That's good because I know.
Jerry, can you help us?
What? I didn't pay attention.
I'm sure there's
Oh,
some
set
How do
both
we
equations equal to each other.
Set the equations equal. They're both equal to y, right?
Oh, Nicolas? Yes.
So 4x is going to equal x cubed plus x plus 2. Alright, so now we can solve this. 0 is x cubed minus 3x plus 2. You say, well, how in the world do I solve that? Well, we can try to factor,
Oh, no, you can't do that.
but here's the cool thing. We already know one of the roots of this equation. Which one do we know? We know 1 will make these guys intersect, right? We know it intersects at x equals 1. So guess what? I'm going to actually factor this I can factor out an x minus 1 using my synthetic division. 1, 0, negative 3, 2. I'm going to pull out an x minus 1. So let's see, 1, 1, 1, 1, negative 2, 0. So that factors into an x minus 1 times x squared plus x minus 2. And then that's kind of cool because x squared plus x minus 2 factors into an x minus 1 times an x plus 2.
So it's x minus 1 squared, x plus 2.
Yes. So our roots are at 1 with a multiplicity of 2 and negative 2. Now, why do you think 1 has a multiplicity of 2?
Because it's going to be.
It would end up being x minus 1 squared times x plus 2.
Yeah. And it's because 2, it's tangent. Remember when we were found zeros, when there was a multiplicity of 2, it just came down and touched the x-axis and went back? It was tangent to it? Well, the thing that makes this line tangent to the curve is that it intersects it with a multiplicity of 2 there, okay? So any tangents will end up working that way, and then the other one is at negative 2. So now we know this point here is negative 2 something, and we just plug it in either to the line or to the cubic, or to both if you want to just make sure, and you'll get negative 8 as the y coordinate. 4 times negative 2 is negative 8. Negative 2 cubed is negative 8. Minus 2 plus 2 is still a negative 8. Okay, so either way you'll get negative 8. Alright, but here I found the coordinates of the point where the tangent line will intersect the curve again. Okay? And that's useful, you know, in applications. You remember we talked about things moving, and if we were traveling along this path, this cubic path, and we lost control right here, we would go on a path that's tangent to the direction. Okay? Well, where would we pick up if we wanted to get back on the path?
At night.
If we just kept walking in a straight line, you know, we would pick up on the path right here. Okay?
And
So.
hopefully your destination's right
Yeah, and hopefully it's not past where you're trying to go or something like
I'll
that.
bring it to you guys. This is math. It's not that easy.
Oh, math is easy. The real life is where we run into more
Yeah,
problems.
that's where we differ, Mr. Hicks.
Because we have more, well, in math class we can control variables, okay? You could be going in that nice straight line and there's this giant cavern or, you know, that's blocking your way, and now you gotta figure something else out. So.
I totally forget how do we do that step, like step on the left.
Oh, the synthetic division?
Yeah.
Okay. You take the coefficients. This was x cubed. We had 0x squares. We had minus 3x, and then you had the number.
Yes.
And then you remember, you add straight down, and then you multiply by what's over here. So
Okay.
times 1. And then you add straight down, multiply over. Add straight down, multiply over,
Okay.
add straight down.
I get it.
And I know it's a perfect root because this came out to have a remainder of 0. This was your remainder. And notice you lose, if you keep it in the columns, you're going to lose 1 power of x in each one. So it was x cubed, now it's x squared. It was x squared, now it's x. It was the x, now it's the constant.
Okay.
And this would have been the remainder.
Yes.
Okay, so yeah, it's been a little while since we've done that, but that is a way that you can solve here. Okay? Alright, now this one is a little bit different, okay? Because we don't know what the tangent point is. This application, we actually want to make sure that we are tangent to the curve, but we're starting at a point that's not at the curve. We're starting at the point 2, 3. Okay? So basically what we're asking is, hey, we want to hit this point. Where is that point that will make a straight line that'll be tangent? This is the kind of thing that back with Apollo 13, you had them orbiting around the moon, and you had Earth over here, and they wanted to make sure that they hit Earth. So they had to figure out, okay, where do we need to get out of the moon's orbit so that the tangent line will take us straight to Earth? And I got the sizes reversed there, because the Earth is bigger than the moon. But you get the idea, okay? But they had to figure out, hey, where's the tangent line on this path? If we're rotating this or going around the moon that way, when should we get out of the moon's orbit so that we're aimed in the right direction? Because they didn't have enough fuel to make some major adjustments. Hey. Okay, so that's kind of the idea that you can behind this. So, what strategy do you think would work here?
Derivatives.
Take a derivative. Okay, there's a good idea. So let's see. dy dx is 2x. All right.
Plug it in.
What are we going to plug in?
Two?
No, 'cause that's not the point,
Yeah, that's
Oh,
2 is
yeah,
not the point of
that's not the-
tangency.
yeah.
unfortunately.
What would we plug in?
A squared.
A. All right. If you plug in A, I know the slope of this tangent line is going to equal A times 2. So 2A. Okay? Now this is the part that's a little different, but how do you think?
It's not that, because if it's a squared equals 2a, then a is just gonna be 2.
Oh, but it's not A squared equals 2A. This is the slope of the tangent line, right?
Mm-hmm.
Okay.
Okay.
Right now we have two unknowns. We don't know what the slope of the tangent line is, and we don't know what A is. So anytime you have two unknowns, what do you need?
System of equations.
A system of equations.
We can create another equation based on the external point.
Okay. Keep going with that. How would we do that?
2x plus, I mean 2, like 2, let's say that like 2a plus b equal to 3. No, I don't mean the a is not the a right here, but I just trying
Oh,
to
the slope? 2 times.
Yeah, 2 times the
Okay, I get what you're trying to use, like the line that it's on.
I don't know how
Well,
to say that.
if you have the slope, you can just use the other point to get an actual numerical slope and then do point slope.
Wait, doesn't they have the same slope?
What
Yeah,
have the
because
same
it's
slope?
Like the tangent line and the straight line.
Those two coordinates.
Yeah.
So could you do y equals mx plus b with the plugged in numbers for both a and 2,3? Or a comma a squared and 2,3?
You could. Yeah, so y equals mx plus b. So you're saying do 3 equals m times 2 plus b.
Yeah.
And also a squared is going to equal m times a plus b. Now we have 3 variables though.
So I just made it harder.
Well, but we have a third equation, right? Because this m is the slope of the tangent line, right?
Yeah.
What does the slope of the tangent line equal?
2a.
2a. So guess what?
It's gonna be 4a and then 2a squared.
So 3 equals 4a plus b. And a squared is 2a times a, so that's 2a squared plus b.
So negative a squared equal to b.
Negative a squared equals b, which I can then plug in here, and I get 3 equals 4a minus a squared. Now we have a quadratic equation that we can actually solve.
There we go.
a squared minus 4a plus 3 equals 0.
-3 -1.
Good, minus 3 minus 1. So a could be
Well,
1 or 3, which makes sense, because if you think about it, look at the graph. If I kept drawing this, there are two tangent lines, right?
yeah.
Because there's a point up here that would also give me a tangent line through the point 2, 3.
Oh, yeah.
So there's actually two different ones, and we actually found the x coordinates of both of those points. So that's going to be the point 1, 1, and up here would give me the point 3, 9. Okay? That's great. And here's the thing, the more, every time you get an unknown, you just need another equation to try to figure that out. Now, if we wanted to keep it to just two variables, another way that we could have done this would have been to say, okay, well, the slope of the tangent line is 2a. I could also find the slope of the tangent line using rise over run.
Oh,
The rise would be a squared minus 3, and the run would be a minus 2, right? Y minus y, x minus x. And now I could set that equal to 2a, and I'd have a quadratic equation again. But I'd end up with the same answers either way. So however you see it is great. We ended up with a system of 3 equations with 3 unknowns. And that's fine. You guys could handle it. So,
it's fine.
okay? So this is the kind of idea that another thing that you can do is if we want to make sure we hit a point, where would we have to get out of or get off the path in order to be able to go straight to that point? Okay? Alright. So at this point, I've got some practice that you guys can work on for the remainder of our time, and can get some good work in here, okay?